since there's such a close connection between the derivative and the integral, one goes ahead and defines the indefinite integral, which is essentially related to anti-differentiation. So let capital F of x be the antiderivative of little f of x, right? So that means that the derivative of capital F of x is equal to little f of x. Remember that capital F is unique up to addition of a constant. So we define then the indefinite integral with the integral sign, but without a limit. And we have f of x dx, where that's little f. So we define that the indefinite integral to be essentially the antiderivative of little f. So that becomes capital F of x. But because there's a freedom of a constant, it's traditional to just add a c to the right-hand side. So by computing a table of these antiderivatives of these indefinite integrals, we can use that table to integrate functions. Nowadays, we use software, but when I was a graduate student, we were still using tables. Okay, so we actually know some indefinite integrals already. So if we start with the power rule, we have the integral, the indefinite integral of x to the n dx. And then what you have to think here is what function, when you differentiate it, you get x to the n. Well, you know the power rule means you drop the exponent by 1. So this must be x to the n plus 1. And then when you take the derivative of x to the n plus 1, you get n plus 1 times x to the n. So there's no n plus 1 here, so you have to divide through by n plus 1. So then this is the antiderivative, and to that we always have to add a constant. So the indefinite integral of x to the n dx is equal to x to the n plus 1 over n plus 1 plus a constant. And it doesn't work when n equals minus 1, right? We have division by 0. So this has to be true when n is not equal to negative 1. The case n equals negative 1 is our 1 over x case. So that's the integral of 1 over x dx. We know that the derivative of the logarithm is 1 over x. In fact, it works whether x is positive or negative. So the antiderivative here is the logarithm of the absolute value of x. And to that, we have to add a constant. So these are our first two antiderivatives, or indefinite integrals. What are the other functions we know? We know the exponential function, so the indefinite integral of e to the x dx. Well, the derivative of the exponential function is just the exponential function, so this is just the exponential function plus a constant. We know the integral, say, of sine x dx. Well, how do we get sine x? Well, the derivative of cosine x is negative sine x. So negative cosine x will give the derivative of negative cosine x will give us sine x. And to that, we add a constant. What about the integral of cosine x dx? Well, the derivative of sine x is cosine x. So this will be just sine x. And to that, we add a constant. So we already know how to integrate some very fundamental functions. Since we know the addition rule and the constant multiple rule, then we know that we can integrate any polynomial now, just integrate term by term. And then we can integrate, the addition of these types of functions. More complicated functions will require more sophisticated techniques, and that's what we'll explore in the next few lectures. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.